There are many definitions for what statistics is. I've read them all, and I find some of them to be either too narrow for my taste, while others are simply too generic. Personally, my favorite is that statistics is the study of variation. We will formally introduce the concept of variation later on, but for the time being, let's just appreciate the fact that if you monitor an event, such as a given traffic light each time you drive through the same intersection on your way to work in the morning, or the minimum temperature at night throughout the year, you will find that certain events tend to be far more predictable than others. And by predictable, I mean the ability to anticipate a given outcome. We all know that traffic light that, no matter what, will always be red when we approach it. And even though we may expect seasonal effects for a minimum temperature at night, unless we consult some weather forecast, it is often quite hard to pinpoint the exact temperature with a certain degree of precision, let's say a 1 degree Fahrenheit. Well, statistics is just that. The process of collecting and analyzing data in order to better understand and quantify the variation in a given event. But what is data? Data is information with context. And by context, I mean that if I tally the traffic light at a given intersection and I report my observation as either red, green, or yellow, those data won't mean much to you unless I provide you with a context as to what those colors represent. On the same token, if I report the minimum temperature at night as a sequence of numbers, they will also mean little to anyone else than me unless I specify the units, in this case Fahrenheit degrees, and the location and maybe the time where I collected them. Data can be expressed by either numbers, names, or just a combination of alphanumerical strings. And they are stored in tables, which in statistics, or more generally in quantitative analysis, we call data sets. But unlike generic tables, data sets, rows, and columns have specific roles and meanings. An important distinction when it comes to data sets is cross-sectional versus time series. A cross-sectional data set shows variable values for several observations at a given point in time, or just collected as a single aggregate over a given period. A time series follows a single variable over a certain period of time by collecting the variable values at specified time increments. The example shown here represents a cross-sectional data set. In this class, we will mostly focus on cross-sectional studies. This statistics course mostly focuses on inferential statistics, which is the process of drawing information from a sample of data points in order to answer questions about a population. A population is the total set of members in a given group, such as the population of US adults, or the population of fish in a lake, or the population of objects being produced by a manufacturing plant in a year. Often, the population is so large and dynamic in terms of composition that it is often impractical, if not downright impossible, to characterize statistically. Therefore, in statistics, we resort to extracting a sample from the population and make inferences about a population from the sample statistics. Later in this course, we will better formalize the concept of sample, but for the time being, let's just say that a sample is just a small data set extracted from the population. For example, the data set shown here represents a sample of statistics students from a statistics class I've taught a few years ago. You can view it as a sample extracted from the population of statistics students I've taught in my career at VCU. Each row of a data set represents an observation. The subject of the observation depends upon the type of event about which we are collecting data. If we collect answers to a questionnaire for a certain survey, each observation will consist of a survey's respondent. If we design a scientific study on human beings, then each observation is called a participant. If the study consists of an experiment on inanimate objects, then the observations are called experimental units. The point remains that each observation of a given statistical study is always stored on the rows of a data set. Many statistics textbooks refer to the entity described by each observation as the who of the study. Consider the statistics class data set. The V numbers are fictitious and have been added for illustration purposes only. In this data set, each row represents one student, or, if you will, the students of the statistics class are the who of the study. Conversely, each column contains information about a given observation. In general, such information consists of attributes, which in statistics are more precisely defined as variables. Many statistics textbooks refer to the variables, the attributes, described in the columns of a dataset as the what of the study. There are two types of variables in statistics, quantitative and categorical. Our textbooks addresses categorical variables as qualitative. Although it is a term often used in statistics, I never really liked the word qualitative applied to a variable, so I will henceforth be using the word categorical instead. Quantitative variables are expressed by numbers and have units. Note that the mere fact that a variable is expressed by a number, it is not a sufficient condition for it to be defined as quantitative. Consider the statistics class dataset. The column labeled zip code reports the residence zip for each student in the dataset. A zip code is expressed by numbers, but it has no units. Therefore, it is not a quantitative variable. If the concept of units confuses you, think of physical measurements such as the temperature in Fahrenheit degree, the height in inches, the weight in pounds, the time in seconds. With all these variables, you can do math with. You can add them together, or you can assign a practical meaning to the difference between two values. With a zip code, you can't. I mean, you can certainly take two zip codes and calculate their sum, but it would not have any meaning. There are several distinctions for quantitative variables, but for the purpose of this class, we should just focus on a couple of them. An important distinction is between a continuous quantitative variable and a discrete quantitative variable. In layman's terms, a quantitative variable contains decimal and it is very dense. Each possible value of a continuous variable may differ from each other by a very small fraction of a unit, and it is expressed by decimals. Conversely, a discrete variable can only assume a finite set of values. For example, GPA and distance are both examples of continuous variables, whereas class score, given the fact it is expressed as a whole number, an integer, between 0 and 110, is a discrete variable. Another important distinction is between a ratio quantitative variable and an interval quantitative variable. As the name implies, a ratio quantitative variables can be expressed to calculate ratios. If you have $100 in our pocket and our friend has $50 in her pocket, we can always say that we have twice as much money as her, because we can divide 100 by 50 and obtain a ratio of 2 to 1. Most physical variables in nature are ratio variables, such as weight, height, time, etc. However, not all quantitative variables are ratio variables. Take in consideration the variable temperature. If yesterday the temperature was 60 degrees Fahrenheit, and today it dropped to 30 degrees Fahrenheit, we can certainly say that the temperature dropped by 30 degrees Fahrenheit. In other words, there is an interval of 30 degrees Fahrenheit between 30 and 60. But can we say that yesterday was twice as warm as today? No, because temperature is an interval quantitative variable, not a ratio one. Put simply, any variable that is not quantitative, it is by default defined as categorical. So all other variables in the dataset shown here are categorical. They can either be expressed by words, alphanumerical characters, or numbers, but without units. There are two main types of categorical variables, nominal and ordinal. A nominal categorical variable is the most common type, and it just assigns a string of characters with a certain context to an observation, without any rank or merit scale. An ordinal categorical variable, which is also called hierarchical, is also assigned through a string of characters, but its possible outcomes are ranked. There is only one example of ordinal categorical variable in the example shown here, the letter grade. Any other categorical variable listed in the dataset is nominal.